All right. So, okay, so now the framework will be a lot more general. And I will talk very generically about minimizing a non-convex, well, a function that I don't know very much about, but for which I may have access to its derivatives. So there is some underlying assumption here that the function is smooth, but just think that maybe I only see function values and derivative values at some given points. So you give me a point, I have a black box that gives back function values, maybe gradient values, maybe second order derivatives.
Sorry, we're talking about only continuous functions?
We are talking for, yes, it's called continuous optimization. So we are talking about that to start with. I will make some pointers to what we haven't covered at the end, okay, which will be very important, what we haven't covered. But time is very, very limited. Now, a lot of you may have never seen optimization. Okay, so I will, hands up who has never seen optimization problems. Okay, great. Okay, you've all seen optimization problems. Good. A lot of you have seen convex optimization problems. Right, right. Yes, you have. Right. Okay, good. So who has worked with non-convex optimization problems? Okay, all right. So I think, especially if you are involved with, say, machine learning applications, you probably would have seen quite a few convex problems and maybe are sort of unsure how to work on, say, deep neural networks where you have a lot of non-convex optimization. And sort of I wanted to sort of have two aims here. One is for the people that maybe have not worked with convex or non-convex, to tell you that, look, if you don't know very much about the function, there are these methods that can still do a lot for you. And for those people that have worked with convex but not with non-convex, my message for today would be we can still do a lot, even if the problem could be very nonlinear. Okay, I'm not claiming we can do a lot to find the global, but at least to finding local solutions. So this is all sort of classical optimization, but this classical optimization has given rise to very powerful software for solving this kind of non-convex, quite black box problems. And so I would try to give you a flavor of the methods and what they can do and what the problems are today. Right, so let's get down to it. So minimize f of x, where x can be in a set and where the number of variables x could be very large. Without loss of generality, I assume I'm minimizing. There's a connection between minimizing and maximizing. So this is without loss of generality. And before I give you a complicated definition, let me give you a 1D example. So here I have a wiggly function, and the question is, what kind of minimizers and maximizers and so on, what kind of minimizers, let's say, does this function have in an interval AB? Right? So if I look at it, I see that, yes, it has a global minimizer here at x1, where f takes its smallest value over all admissible values, which for me are the interval AB. Then I see that at this point, something interesting happens, because around this point, f takes its smallest value in a sufficiently small neighborhood, right? And this is what we refer to as a local minimizer, right? Okay. Do I see any other points that may have a connection to minimizers? I'm waiting. X1 I've talked about, X2 I've talked about. Yes?
Well, the slope of the gradient is like goes to the left, like near A on the boundary.
Right, very good, very good. So at x equals A, indeed, if I think of my admissible solutions or my feasible solutions, so x in AB, right? At this point, f takes its smallest value if I restrict it to x in AB. That's right. So this is a constraint minimizer, local minimizer. Right. So indeed, we can formalize these things and say that we have a global minimizer if x takes the smallest value in omega. We have a local minimizer if there is a neighborhood around this point where f takes its smallest value when we intersect it with the feasible set, where this neighborhood, we are in Rn, so we can define it with, say, the Euclidean norm. And this local minimizer here, because I intersect with my feasible set, corresponds to both the ones that were constrained in this picture, so x equals a, and the ones that were not really constrained. Okay. So that's sort of a very, very general definition. It can apply to pretty much anything. All right. So what kind of other problems can we have? Well, anything can happen once you go above 1D, right? So you can have very, very nonlinear landscapes, or you can have sort of banana-shaped valleys that are very narrow and sort of hard to get into. And we'll come back to some of these examples. But in optimization, what we do, and this is maybe one sort of fundamental fact that I would like you to come away from today with, is that we think of problems on classes. So the more you know about the structure of your problem, the more you should try to use that in the algorithm development, of course, for better efficiency. So if you have a linear problem, like Raphael talked about earlier, where you minimize an objective that's a linear function of the variables and you have linear constraints, then finitely many of them, then you should solve that as a linear programming problem rather than use all this machinery I will talk about in the next few slides, because you will be able to get better efficiency. So what I'm talking about, for example, is if you have a linear problem, go and look for a linear programming code rather than a nonlinear programming code that will not already recognize that this is a linear problem. Similarly, if you have a quadratic problem, so you have this here a quadratic term where this matrix H is independent of x, then solving that as a quadratic problem can help in efficiency. And there are some more sort of intermediate classes, but sort of these are sort of the simplest problems that you can have in optimization. So linear or quadratic in the objective, and linear constraints. And then sort of the talk today will be more on nonlinear problems, constrained or unconstrained. So unconstrained, I mean there is no restrictions on x, and constrained that you have finitely many equalities or inequalities, and these constraints could be non-convex. But mostly today I'll talk about the case when all of these functions involved, f and ci's, are all smooth. Right. Okay, so some simple, very quick illustrations. For example, if I have a network, say this is a real representation of a gas pipe network that takes the gas from the North Sea and pumps it out across a high pressure network across the UK. And in this framework, you have the pressures and the flows are your variables, and the demands are yours. You can assume they are given. And so you try to find out how much you should pump across each sort of pipe and at what pressure, so that you satisfy demand. And so you have this kind of constraints at each node, where A is a sort of a matrix that's very sparse and has plus or minus ones and corresponds to the flows at the nodes. Then you could have then you have this kind of relationship between what's the connection between flow and pressure, and you see that the engineers have done a lot of experimental work to precisely find a connection between the pressure and the flow of gas in a pipe, and you see that they connect as in this sort of funny way there. Okay. And then again, what you need to have is some kind of compressor machines at various points in the network, various locations in the network, that boost the flow in the pipes, because otherwise this would stop and it wouldn't reach where it has to reach. And the compressors are expensive to run, and so you have to sort of decide when to run them, which ones to run them. You also have a lot of bound constraints. This you often encounter in real life, this kind of simple bounds on the variables, outside of which you may have problems. You really have to satisfy those kinds of bounds. So this is a sort of a set of linear and nonlinear equations and bounds that is sort of quite typical of problems. You have some kind of sparsity in the linear algebra that you have. And you can have various objectives. You could minimize the cost of running the compressors and so on. So this problem, if the demand is known and constant, then you have, say, 200 nodes and pipes, 400 variables. Okay, it's not too bad maybe. But once you start to allow, for example, for stochastic demand, or you want a real-time solution, because of course the demand is going to vary throughout the day, then this problem grows in dimension hugely. So we are talking here about methods that could tackle these kind of problems, and especially this kind of increase in scale. Another problem that would sort of be more like that you need maybe more specialized methods going beyond what I will talk about here, but still what I will talk about here would form the core of the methods for these problems as well, is this kind of heavy nonlinear problem called data assimilation, which the Met Office has to solve a few times a day. And what this problem does is, so you have to find an accurate representation of the state of your atmosphere at a given time so that you can run the weather forecast forward in time. So you are, say, at the end of a previous forecast, and you have to recalibrate whatever you found at the end of that forecast to be the state of your atmosphere. So you have to calibrate that value against whatever observations you have had come in while you were running your previous forecast. So you have some additional observations, but you still don't have enough of them. So you have these yi's are the observations at a few time slots. You still don't have enough of them compared to how discretized the state of your atmosphere is, which is in that range. Okay, so X is huge, and what you do is you do a few forward time steps from your current state of the atmosphere, which is your unknown, right? And at each time step you have a different state of the atmosphere, but you know how it connects to the initial condition, essentially. And so essentially you solve this inverse problem, or think of it as a data fitting problem, but it's of a huge scale. Now this is ill-posed because, as I said, there are more unknowns than observations, and so what you usually do is you regularize here by some quadratic term depending on the solution of your previous forecast. So this is a nonlinear, non-convex problem, and these non-convex methods are the basis for what is being used for this. Okay, so these were just really to give you some illustrations of this kind of non-convex problems that I will mainly speak about. Right, so now let's start talking about methods and how do we, and in fact before we even get there, I want to say a bit more about how do we characterize solutions of optimization problems. So until now I've just said, well, it takes the smallest value in a neighborhood, or maybe the smallest value over the whole domain. But can I characterize these solutions in a way that I could use in computations? And this is where derivatives are very useful. So if you remember the previous 1D plot here, right? A simple way to characterize this kind of points is that the first derivative there is 0. Right, so indeed, for smooth continuously differentiable functions, At a local minimizer, you always have a 0 gradient, and we call such point a stationary point. Right. Okay, so why is it that the gradient is 0? So let me try to give you a little bit of connection here between these optimality conditions and what does it mean to be able to make progress from a point or not. So let's say that I have a function and some point x and s, where s is a direction. I think of s as a direction that's non-zero. Then if the gradient of f transpose s is less than 0 strictly, so this inner product is negative, then I'm guaranteed to be able to decrease f from my current value at x along this direction s for a sufficiently small alpha. So alpha is a scalar. I have a point x that is fixed, and I have a direction, a non-zero direction. So if I have this property that the gradient of f transpose s is negative, then I must be able to decrease, my function will decrease along this direction s for alpha sufficiently small and positive. Okay, I don't have time to give a proof, but it's quite easy to prove this using Taylor expansions, first order Taylor expansions. Right, so how do we interpret this? Well, we call such a direction a descent direction because of this property, really. And then if I rewrite this, in fact, what this gives me is that the cosine of the angle between the direction s and the negative gradient is positive. So the negative gradient and the direction s forms an acute angle. And here's some contours of my function f. Here's the negative gradient and some direction pk that is descent, and that forms an acute angle with the negative gradient. In fact, the negative gradient itself trivially can be shown to satisfy this property whenever it's non-zero. Right? So in other words, what are we saying here? The negative gradient is always a descent direction for my function, unless I'm at a solution, at a local minimizer. And any direction that's not too far from the negative gradient will also give me descent. Okay, so we've learned a couple of things already. If the gradient is not 0, I can move along the negative gradient and decrease my function from my current point. If it's 0, I am at a stationary point. Maybe minimizer, maybe not, we'll see. And so, any descent direction is essentially close to the negative gradient direction. But the gradient is also 0 at maximizers, right? The trivial 1D plot showed that. So to distinguish minimizers and maximizers, I have to look at higher order derivatives. Okay, so in fact, what am I looking for? What kind of property tells me if in a simple 1D plot, if I have a minimizer or a maximizer? Okay, second derivatives, yes. And what kind of property? What is that telling me about my function, right? No. No. So it's whether the function is convex or concave. So if I have a 0 gradient and I have local convexity, then I have a minimizer. If I have 0 gradient and local concavity, I have a maximizer. If I have a 0 gradient and I have directions that along which the function is locally convex, and I have directions as well along which the function is locally concave, then I have a saddle point.
Can't I just show it by looking at the previous and the next value?
Sorry?
Can't I just say that by looking at one previous value or the next value? Assuming that I'm in local maximum or minimum, I'm looking at the next one.
Yes, but if it were your global, yes. But if it's local, how do you know if you're sufficiently close?
I don't know if I'm a maximizer or if I am a minimizer. I'm in the local maximum or local minimum based on the two previous values, or the next one and the previous one.
It's not so simple. It's not so simple. So essentially, I have to have some kind of notion of, I have to have local convexity to guarantee that I have a minimizer. But I can ascertain this kind of local convexity by looking at second derivatives, right? So if I have a second derivative that is positive semi-definite, then I have local convexity. So this property of second derivatives, whether this matrix is positive semi-definite or definite, this is connected to the convexity or otherwise of the function. Right. Okay, so how do methods for this kind of problems look like? Right. So I will talk for the next few slides about unconstrained problems. So I minimize a function without any restrictions, and in my algorithm, I'm going to choose a generic accuracy to which I want to solve my problem, and I'm going to choose an arbitrary starting point. While my termination criteria is not satisfied, I will improve my current estimate. So I will generate an estimate x1 of a minimizer, and using problem data, and update my current iterate, and I will try to ensure at least that this is that at the next point the function goes down, or at least this doesn't worsen. And then I will consider this as my best point found so far. So a termination condition would be based on the optimality conditions that the gradient is sufficiently small, and maybe that at least I have a sufficiently positive, almost positive semi-definite matrix. If it's positive definite, it's great. But sometimes I'm even happy with something slightly weaker than that. So what these methods do is you cannot guarantee that you get a global minimizer with them. Because they use derivatives, and because they use derivatives in the termination conditions, you essentially cannot say that you can only guarantee that you found a stationary point, usually, hopefully a minimizer. You will essentially always be able to improve your function value from what you had at the start. But the other aspect is that we will try to allow that the initial point can be anything. Now, how do we generate this point here? Where usually, because we don't know how this landscape may look like, and it could be in very high dimensions, usually we will approximate our function by a simple model, for example, linear or quadratic local model, and minimize that instead of our function. So the next guess is constructed by approximating our function f by a simpler model. And this is what the main methods in this area do. Line search and trust region frameworks, this is essentially what they do. They only use information at the current point xk to construct the next iterate xk plus 1, and this information helps build a linear or quadratic model. So the kind of questions we ask about these methods is, can we guarantee that from an arbitrary starting point, these methods converge at least to a stationary point of our objective, or at least that the gradient at the iterates converges to 0. Maybe you can, for some methods, you can say something about second order conditions as well. But sometimes you cannot say maybe something about global convergence, but you can say about local convergence. If you are sufficiently close, will the iterates converge? Or what happens to the rate of the method when you are sufficiently close to the attractor x star? And the other question you want to know is not just that these methods converge, but you want to know how fast do they converge to a solution. Because yes, I may know that in principle, these methods will get there, but if I have to wait forever in front of my computer, until next day, maybe that's too late for me. So these kind of questions of complexity or global rates of convergence answer this question of how long will it take to reach required accuracy. So it's a more refined convergence analysis. And just to illustrate to you that rates of convergence are important, So these are 3 sequences, and they all go to 0, but they go to 0 at different speeds. And in this plot, you can see this sequence here, the QK sequence here, and the SK sequence here. And in this plot, this plots the K value versus log of the sequence. And what you can see is that within about 10 iterations, log of QK reaches this target value, say, SK within 70, and LK is still going. And you can see here, this is, you can look more at it later. Essentially, the linear rate is the case where the error decreases by a fixed amount in each iteration. Quadratic rate, where the error decreases exponentially, where the number of correct digits double in each iteration, essentially. So that's very, very fast. But I should say that linear rate, though it's much worse than quadratic in here, is usually very good, provided this fraction here by which the error decreases is not close to 1. Right, so this is just a refresher of rates if you don't remember them. Right, so now what I will try to do in what follows is I would like to give you more ingredients in this generic method. What is in there? How do we generate the next guess of the solution so that we get convergent methods? Right. So a line search method is built around 2 ingredients. One is that generates a descent direction at each iteration. And then it's going to calculate a step size along that direction to make sure that at the next point we decrease our function value. So descent direction, I mean exactly this property that we had here, that we've seen. So we somehow calculate an SK such that this is satisfied. We've already seen that the negative gradient direction is going to be such example of an SK that will satisfy this. And once I've computed my SK, then I'm going to calculate this alpha k to decrease my function. And then my next guess of the solution will be this new point. Right. So are these 2 steps compatible? Based on the lemma we've seen, if SK is descent, right, we said that then it's guaranteed that f will go down from xk along sk, provided alpha k is sufficiently small. So once I have an sk like this, there will be an alpha k, positive, sufficiently small, such that this is satisfied. So indeed, these 2 can be achieved because of the lemma that we've seen. How should I compute my step size alpha k? So I assume that I've computed my sk. I will come back to this. How do I compute a good sk? And what is a good sk? But let's first just deal with the question, assuming I have a descent direction sk, how do I compute the scalar alpha k? So sk is my direction, is still in Rn, but alpha k is just a scalar. So in principle, this should be easier to compute. So if I have my sk, then I could compute my alpha k, say, by what's called an exact line search, where I minimize my function along this direction. So I've reduced my n-dimensional minimization to an 1-dimensional minimization per iteration. But that is still, in the case of nonlinear functions, this is still potentially very expensive. So this is essentially never used in practice unless you have, say, a quadratic function where you can compute this exact line search exactly. So apart from that case, and here you see an illustration for quadratic functions. I won't have much time to go into it. But essentially, I will do 1-dimensional minimization along a given direction of my function. Too expensive usually. So what people do is something that's called an inexact line search, and this is what all codes do, where instead of requiring some kind of the best decrease we can get along a certain direction, all we ask for is some kind of sufficient decrease. And these can come in various forms, and I will just give one here for illustrations. The details are not very important unless you really need to sort of learn this for your research. So essentially what we do is we say that I want to decrease my function at the new point to be lower than this right-hand side here. So I want to compute an alpha k that satisfies this property here. And OK, 0 satisfies it, so I don't want that. I want the largest alpha k that satisfies this. Now, this term here is negative. This beta is a fixed constant. So this is negative here. And so this is strictly less than fxk. Right? So if I satisfy this, I will definitely decrease my function from the current value of xk. But moreover, I will decrease it by a somehow sufficient amount, namely an amount proportional to the length of the step. This will prevent me from taking steps that are long but do not give me enough decrease in f, which is often otherwise a cause for failing to converge. So one can show that there is an acceptable interval always for which this can be satisfied. So what we do is we can start with some arbitrary guess, alpha 0, and then we keep reducing that guess until we satisfy this property. So that's kind of simple backtracking. Okay, so this requires for every guess of alpha k that I try to satisfy this property for, this requires calculating an additional function value. So this line search is not cheap. It's much cheaper than exact line search in general, but it doesn't come at no cost in terms of evaluations, of course. The other thing to say is that I just want to make sure that it's clear that this kind of line search procedure, I have to apply it in every iteration k. So it's like an inner algorithm inside my major iteration. So at every k, I have an xk, I have a direction sk, and then I do this kind of inner iteration to compute an alpha k. Right. I've given more explanations here as to what this Armijo condition means graphically. Essentially, if I think again univariately, so I think of my f along alpha as just a function of alpha, because this is exactly what it is, because xk is given, sk is given. Those are fixed. So if I look at it as a function of alpha, here's some simple f, simple phi to be correct. And then what this right-hand side of Armijo condition is nothing but a line that is between the tangent to my xk, and some line parallel to my alpha x-axis. So this line will always be guaranteed to intersect the graphic of my function f. And so what I'm looking for, what would be acceptable values for the Armijo condition would be something in this interval here. So any alpha between 0 and 0.9 would satisfy the Armijo condition. So all I want is to find an alpha in that interval, usually as large as possible. Okay, that's a sort of a simple condition. Most line searches have maybe another additional condition. Okay, so line search, we do it with this kind of inexact line searches in all codes. So now let's talk a little bit about direction. How good is the steepest descent direction, for example? So what we mean by steepest descent is nothing but what I hinted at, namely the negative gradient direction. So we've seen that that is a descent direction. Why do we call it steepest descent? Because it is the direction along which f decreases at the fastest rate locally. And we see that by looking at the fact that the negative gradient is the solution of this minimization problem, minimizing a linear model of my function around the current point xk, subject to some length constraint, because if I didn't have this length constraint, what would happen? So this is a function here in S, okay? This is known, this is known. If I didn't have this constraint here, then the solution of my problem here would be minus infinity, because it's a linear function in S. And if I minimize it over all of Rn, it would give me infinity. So I need to somehow fix the length, okay? But whatever I put there, it would give me a multiple of the negative gradient. Right. So I said to you that what we do is we approximate the complicated function f by some simpler models. Indeed. With steepest descent, what we mean really is that we approximate our function f by a linear model, linear Taylor model. Okay. and you can see that this negative gradient is indeed the solution if you look at Cauchy-Schwarz inequality. So when we talk about method of steepest descent, all we mean is that is say line search method, or it can have other techniques than line search, but it's a method where the direction along which we go downhill is the negative gradient direction. Now, if I take a line search framework and I do my line search exactly or inexactly, and I take as my direction the steepest descent on each iteration, then I can give this kind of guarantees of global convergence. So let me explain to you what these are. So if I have a function that's continuously differentiable and bounded below, and the gradient is Lipschitz continuous, okay, what does this mean? So it means that the change in the gradient can be bounded by a multiple of the change in the argument of the gradient. Okay, so I can somehow control the length. This is always true if I had if this function was over a bounded domain. This would always be true if the gradient was continuous. And it is often true, for example, if f is, give me an example of a function with a Lipschitz continuous gradient. If my function f is constant, is this true? Yes. If my function f is linear, yes. If my function f is quadratic, if my function f is quadratic, let's say f of x is, right, then what is my Lipschitz constant? So, right, so, okay, so let's write. So, okay, so if I write that Lipschitz property, what do I have? Age x minus age y, right? So this is the same as age. Age is a matrix, right? So this is less than norm of age times norm of x minus y, right? So this is true. Okay, so all those functions satisfy it, and in fact there are many functions for which this is true. For example, if the second derivative matrix is bounded on Rn, then this is always true. It's the same kind of thing. So in that case, steepest descent is globally convergent. I have made no assumptions on the convexity of my function. It could be given to me in a complete black box, all right? And steepest descent will converge from an arbitrary initial guess. This is a very, very large class of functions for which we can guarantee that this method converges. So this is a very, very weak assumption. So this is all great. However, there are some problems with steepest descent. And because at the moment, first order methods and sort of gradient based methods are very popular, I do want to point to these issues, because I do want you to sort of be aware, because all methods that use just first order information will just gradient information in a simple form like steepest descent will suffer from this kind of problem. Steepest descent methods are scale dependent. So what does this mean? It means that if I have a function, so I'm illustrating here on a simple quadratic. So I have a simple two-dimensional quadratic function with coefficients a and 1. Okay? So this problem is well scaled if so a problem is well scaled if when I change one of the coordinates by a small amount, the function changes by a small amount. So in all coordinates this happens when I make a small perturbation along one coordinate. However, it's not well scaled if when I change one component by a small amount, the function changes by a small amount, but when I change another component by the same small amount, the function changes by a huge amount. So for example, if I have a function that measures some things in centimeters, some things in kilometers, right? This is not going to be a well-scaled function. But multi-scale kind of processes, essentially are always suffering from this kind of problem. You have to be careful when you include them in the same objective. So here, right, if A is much, much larger or much, much smaller than 1, then when I change, let's say A is much, much larger than 1, then when I change x1 by a small amount, f is going to change by a huge amount compared to when I change x2 by the same small amount. Right, okay, so what? Well, the problem is that the gradient direction inherits the poor scaling of the function. So here's the case when A is like 10 to 0.6, so it's not really badly scaled. And you see here the steepest descent iterates. So to reach decent accuracy, I will take a lot of iterations with steepest descent. If the function is well scaled, in particular if A is 1, so this is perfect scaling really, then I take 1 step to solve the problem. So the number of iterations it takes for the method to reach the solution depends on the conditioning of the problem. And in particular, this direction is adversely affected in the case of steepest descent. Okay, so this is connected to another issue. Namely, yes, steepest descent converges. But it converges very slowly. And that, if the problem is even mildly poorly scaled. It converges slowly, and you see that usually. This is not a rare occurrence, it's common. So this can be quantified quite rigorously, but I don't have much time. So the asymptotic convergence is slow. So I'm not even talking here about when I'm very far away from the solution. In fact, steepest descent then is pretty good, all considering that I'm far away. But when I get close to the solution, it can be bad. So what do I mean here? When I'm close to the solution for steepest descent, I have linear rate of convergence. That is not bad, okay? So f decreases at a linear rate, so it satisfies an error decrease of this form, where rho here is between 0 and 1. So this is no problem. The problem is that for steepest descent, this rho is very close to 1, okay? Very often, depending on the conditioning of the problem. If the problem is well conditioned, this is fine. It's not an issue. But once the problem starts to be poorly conditioned, this rho gets close to 1 quickly. So here I illustrate the behavior of steepest descent with line search on the two-dimensional Rosenbrock function. This function satisfies the Lipschitz continuity property, okay? Steepest descent converges on this example in theory. But in practice, the rate is so slow that the method breaks down. Okay? So I just want you to bear this in mind, that steepest descent by itself, though in principle reliable, can be very, very slow depending on the conditioning of the problem. So we need to have better methods, that's for sure. Steepest descent will not be enough. And what we need to do is, we saw that the problem with steepest descent was to do with the scaling of the problem. So let's try to scale the direction. So let's consider directions as k that are of this form, where bk is some matrix here, and think of it as bk could be diagonal or not, and it would provide me with essentially a scaling of steepest descent. All right? So let's try to, even if the problem is bad, let's try to locally rescale my steepest descent direction to make this direction good in the presence of your conditioning. So how do we do that? Well, if bk is symmetric and positive definite, one can show that this gives me a descent direction. This is one thing you could try to prove by yourself, because it's not very hard. So if bk is symmetric and positive definite, I have a descent direction. Another way to view this equation here, that I just sort of pulled out of a hat a little bit, is as the solution of this kind of problem in S. So steepest descent was approximating my function by a linear Taylor model. Now I'm going to approximate my function f by a quadratic model. All right? So I keep my gradient, my f values there, and I have here some matrix bk. If bk is exactly my Hessian matrix at xk, then this is a second order Taylor model. And then does anybody know what direction this would be? Newton. Okay, so if you haven't encountered this, so if bk is exactly the second derivative matrix of f, then this would give us what's called the Newton direction, and we will see that that direction is actually very fast locally. All right, so okay, so think of this kind of direction as the solution of this quadratic model. But remember here that this bk is symmetric positive definite. So, and is sorry, there should be no sk here. Sorry, that's a typo. So minimizing this model as a function of s, right? It's a quadratic, and in particular, it's a convex quadratic when bk is symmetric positive definite. All right. So because it's a convex function, then the minimizer is always well defined, and it has a minimizer. It has a minimizing direction, and it's bounded below. However, if bk is not going to be symmetric positive definite, then I may not be able to just minimize this direction. In particular, when f is not positive definite or semi-definite, then I may not be able, if I, to get a descent direction from the Newton direction. Okay, now the amazing thing is that if I do this, things improve very much. In particular, I can make my method to be scale invariant. So the behavior of the method will not be affected by linear or affine transformations of the variables for certain choices of bk, such as the Hessian, right? So Newton direction is famously affine invariant. The other property is that this, for example, with bk again being the Hessian, then the local rate of the resulting line search method is quadratic. So we've gone from a linear asymptotic rate to a quadratic rate. But Newton has its own problems. So think of this bk as an approximation of the Hessian or the true Hessian, right? So what am I doing here? I'm bringing in second order information, second order derivative information if I can. So what can we say about the convergence of these methods? Is like before, I have a Lipschitz continuous gradient and so on. However, I have to have another assumption, that these matrix bk that I have in my model and in my direction that I use to calculate my direction in each iteration has to be sufficiently positive definite. Has to be bounded above, okay? That's not such a restrictive condition because it doesn't require convexity or anything like that. But it has to also be sufficiently bounded below, away from 0. Okay, as long as this bk is separate from my Hessian matrix, I can maybe construct this in some way. But if my bk coincides with my Hessian matrix, this is telling me that Newton's method globally is only going to be convergent if I have local convexity at my iterates, and sufficiently good local convexity. So that's a problem. And indeed, there are many, many examples where I just can't keep going with Newton's method on a general non-convex function because I will not have a positive definite Hessian at my iterates. So I'll get back to what do we do then in these methods. But I want to illustrate that on this same Rosenbrock function on which steepest descent was failing to converge, Newton's method converges quadratically if I'm sufficiently close to the solution. But as I said, Newton has its own problems because far away from being sufficiently close, I really can have serious problems with Newton. In particular, I may just be unable to apply Newton's method because it won't even give me a descent direction. So we've resolved some problems and we sort of broken other problems. Huh? Right. So what do codes out there that are based on line search methods do? Let's say you have a function for which you have gradient values, you have second derivative values, and then of course you should try to use them in the algorithm because you will get best performance if you use as much problem information as you can. However, so I use my Hessian, but let's say that it's not positive definite, and so if I just calculate this kind of SK, Newton, it as Newton, I will not even get descent. So what codes do is they modify this method by some matrix MK. So what do you, there are many approaches. How should you choose your MK? Right, it's quite heuristical. But one thing that's very often used is you try to factorize your matrix using, it's a symmetric matrix, so you can try to do Cholesky, but Cholesky will only, or LU decomposition in other words, this method will only work if the matrix is positive definite. So you try to factorize your matrix, and if, so that you can solve this system, and if the factorization breaks down because you can't pivot, for example, then you modify your pivots. You make them positive so that you can continue your factorization. So that essentially boils down to choosing an MK to fix this problem of a negative definite or indefinite Hessian. This is sort of the most popular choice, but there are other options that one can do. So it's quite heuristical. How do you fix Newton's method? There is another way to choose BK, either because you don't have the Hessian, or so in the case when you don't have the Hessian, or in the case that you don't want to do this kind of heuristical fixes. And this is what's called quasi-Newton methods. So these are some very, very clever methods, and they do represent the state of the art for unconstrained optimization, at least some of them that I will mention in a moment. So what you do in these methods is that we are still in this generic line search framework, and after you compute your direction from a system of this form, you construct your next iterate, and then using this and maybe some additional problem information, you construct your next matrix BK plus 1. So you have a way to construct better and better matrices BK. And we view these BKs, of course, as approximations of the Hessians. All right, so how do we do this? And first of all, what would we like? Well, first of all, I don't want to have to compute a lot more additional function information to compute my next matrix BK plus 1. So in fact, all I will do is I will compute one more gradient value that I would compute anyway because it's my next guess of the solution. Now BK plus 1, I will choose it symmetric because it approximates a symmetric matrix, and at least it should be non-singular so that I can solve this system in the next iteration. Ideally, it should be positive definite so that I can have a descent direction. So these kind of methods give rise to methods that are faster than Steepest descent, cheaper to calculate than Newton, that work in the presence of non-convexity. And they are slightly slower than Newton per iteration. They are not quadratically convergent. They are just superlinearly convergent. But they are faster than Steepest descent. So one thing that all these methods require, so I want to find out how should I calculate my BK plus 1. Given BK and given my xk, my direction sk, and my next guess xk plus 1. So what we try to do is construct BK so that it matches the change in gradient. So BK plus 1 applied to the change in the point values matches the change in gradient. If I divide it here by this, and if these points were close together, this would be a clear approximation of my Hessian, right? The Hessian is nothing but the infinitesimally small changes in gradient, right? But here it's not quite like that because these points could be further apart. However, this property is always true if the function was quadratic and if bk was my Hessian. So I'm trying to sort of mimic a sort of local Taylor model. But these are just n equations for bk plus 1. But my bk plus 1 is a matrix. So I have, it's a symmetric matrix, but still I have order n squared and unknowns. And so just this kind of sequent equation will not be enough. So what we do is we take up the freedom in bk using other techniques, such as my next bk plus 1 is going to be just a rank 1 update on bk, or a rank 2 update on bk. And this gives rise to this kind of very popular methods, symmetric rank 1, BFGS, and so on. So BFGS constructs a positive definite approximate, bk plus 1 in each iteration if you start with a positive definite bk. And it is, in its limited memory implementation, it is the state of the art for unconstrained optimization. The other thing that we can do is, because a lot of these updates are rank 1 or rank 2 updates, we can use the famous pseudo-inverse formula of Sherman-Woodbury-Morrison formula to show that, in fact, when you try to solve the linear system for the direction, so when you try to solve this, usually you would have to factorize this matrix and solve this as a linear system. But because you with Quasi-Newton methods, you just update this at each iteration, you can show that you can invert this in just order n squared than n cubed iterations. Operations. So the work per iteration is much cheaper as well. And they are superlinearly convergent locally. So these are some very interesting sort of hybrid methods sitting between steepest descent and Newton. Okay, how are we doing here? So I've told you about this general framework of line search methods, where we try to have this kind of descent direction on each iteration and compute a line search. And we decrease the function on each iteration, usually by a sufficient amount. We also saw that we can have various methods in this class. Some are sort of first order, some are second order methods, and then there are sort of these in-between methods that are that use just first order information but are able to give us faster rates than just steepest descent. So all these methods were using this kind of line search idea to make sure that from an arbitrary starting point we converge to a stationary point. Now, there is another main class of methods called trust region methods that don't use any line search at all, and that have sort of a more built-in way of dealing with local non-convex models. So I would like to talk to you a little bit about this, and then I would like to talk to you about constraint optimization. Right. So we are still going to talk about this kind of model, right? Okay, so I have this kind of local model that approximates my function f. I told you that if bk is not positive definite, I may not even be able to minimize this model with respect to s. Or the resulting direction could be uphill, or I can have an unbounded below model. So this is a real problem. This kind of, if this is, for example, the Hessian, this will often happen because the Hessian will not be guaranteed to be positive definite. So what trust region methods do, they say the following thing. Actually, this is a local model of my function. Even think of it with Taylor in mind, right? So I have a second order Taylor approximation of my function. This approximation of f is not going to be accurate unless I'm sufficiently close to the point where I'm constructing the approximation, here xk. So indeed, I should only trust this approximation in a region delta k. If I knew a lot about my function, I could construct this delta k precisely as a region where this model would be a good representation of my function. Of course, I will not know this a priori. But still, I say, I'm going to just trust this local model in this kind of ball around my current point. So what is this? When I write this, it just means that I have a ball constraint around my current point xk, because I think of x essentially as xk plus s. So I minimize my quadratic model subject to the points being in a ball centered at xk of size delta k. Now, what is the advantage of this? Well, this is a compact set. It's a bounded closed set. So this is a continuous model. So this will always will have a global minimizer. That will give me descent in the model. Okay? So when I decrease my, so I can always minimize this model because of this constraint. Okay? And moreover, I can do that even when the model is non-convex, right? And you could say, but hold on, this could be very hard. Indeed, but we can do it, actually. We can do it and solve this to even global optimality. So find a global optimizer of this quadratic model subject to this constraint, provided this norm here is the Euclidean norm. And we could even allow approximate solutions of this. Okay. So I can always minimize the model, right? So let's say Sk is the solution, the direction that minimizes this quadratic model subject to this region in which I trust my model. Okay? So what could go wrong in this method? We don't know delta k. That's right. That's right. So because we don't know exactly in what region I should trust my model, what could happen is that if delta k is too large, yes, I've minimized my model, but have I decreased my function at the next point? So that indeed may be the case, that I may not be able to decrease my function. But before we go on to that, let me illustrate a little bit. So here's the contours. The dotted contours are my original non-linear function. This point here is my current point xk. This is the trust region ball, okay? And these contours, the continuous contours, are my quadratic model at this point. So what do I do in the trust region? I minimize these contours. I minimize this quadratic in this ball. So what is the minimizer in this case? Well, we can see that the minimizer of the quadratic is here. It satisfies the trust region constraint. So the global minimizer of the quadratic is the solution of our trust region subproblem. Okay, and you can see that it's probably going to give me decrease in f as well from the other contours. But this is a convex quadratic, right? So my model is convex there. Now what happens is if I have a linear model, I could have a linear model, bk could be 0. Then you can see that it will decrease, the contours will decrease on this ball constraint, and the minimizer could be somewhere here, right? The global minimizer over that ball. May decrease my function, barely. Now here I have a quadratic model, local model, that is not convex. But you can see that over the ball, I can still, minimize this. It's going to be bounded, no question, by Weierstrass theorem. And you can see that you can minimize this in this ball, and you would get some point somewhere here, right? Right here. And also possibly this, if you can see that it will decrease my function at the next point. Now, here we have another convex model, local model, but the global minimizer of the model is outside the trust region. And so here again, the minimizer will be somewhere on the boundary of the ball. So this is how these kind of trust regions and both constraints can relate to each other. Right, so what should I do in my algorithm? Okay, so maybe I've come up with a good idea to have this kind of local, a new kind of approach to local models. But how should I control my algorithm? How should I control the size of the ball to make sure that when I decrease my model, I also decrease my function? All right, so this is what we do. We measure if at Sk is either the precise minimizer of this trust region subproblem, so minimizing this model subject to the trust region constraint, or an approximation of it. Right. So first of all, when I minimize the model, this will always decrease unless I terminate, will give me a value lower than f at xk. So this term here will always be positive. Okay, but the problem is that I have to see whether this term is positive or not. So we check the value of f at xk plus sk, and we see whether the function decrease matches the model decrease. If it matches it by, say, 0.1, I like this step. I've decreased my model, my function has decreased, so my model is a good approximation of my function, everything is good, I've gotten decrease in f of the same magnitude as the model, so I'm going to take the step, and either I keep my trust region at the same value or I may even increase it. However, if the function goes uphill at the next point, right, it means that I've trusted my model in too large a region. And then, of course, my function goes uphill. I can't take this point because I will not even get a better value than what I have. So I stay at the same point, and all I can do is to shrink my trust region. Okay, so I've given you a description of the algorithm in detail, and you can show under very weak assumptions that this method converges. In particular, no convexity assumptions on BK, and the flexibility in these methods is that you will see in the moment, it allows you to take the Newton step. Now I want to show you an illustration. Okay, so I'm going to illustrate how this method works. Right, I have a non-convex objective, and here are my contours of the objective. Okay, so I'm going to try to minimize this with trust region. So here's my quadratic local model. So here's my starting point. Sorry. Here's my starting point, and here's my initial trust region, delta k size 1. I mean, I have to start with something. Okay, there are sophisticated choices in codes, but you can start with 1. There's nothing preventing you from doing that. So at the starting point, any starting point, trust region of 1, I get a local model around this point, quadratic. This is it. And here is the nonlinear contours juxtaposed with the quadratic contours. And then I minimize the quadratic over this ball approximatively in this example. So I won't always get quite the best obvious point. So here I get some point like that red dot. Okay. So I go there, I compute my next function f, and then I compute this rho, the change in f over the change in the model. And I get that it's close to 1. So the decrease in my model agrees, the decrease in my function agrees with the decrease in my model. Very good. I take the step, and I increase my trust region radius. I have to allow increases from time to time in this radius, because otherwise the steps in the run of the algorithm will become unnecessarily small. Why I allow increase? Because I say, well, it's close to 1, so I'm in a good region. I have a good local model. I trust it. So I will explore a bit further. So here's the next. Now I've moved to the next point, right? And there I construct my local quadratic model. Now I have a larger trust region constraint, and I minimize this quadratic over this ball. You can see from the colors of the contour, the minimizer is going to be somewhere here. I do approximate minimization, I get something there. Again, I construct my I evaluate my f at the new point. I get this much smaller value, right? Wow, the decrease in f is even better than the decrease in the model. That's great. I take my step. I increase my trust region again. So I've moved to the next point. Now, at this point, my local quadratic model has become non-convex. Until now, I had a convex quadratic model. This is non-convex. See, the Hessian is indefinite. So I am at this point, and I have this local model, and I have this very large trust region constraint. So now I evaluate my f, and what do I find? That f has gone up from my previous fxk. And that, of course, then in consequence, rho is negative. All right, so then this means I've trusted my model in too large a region. Okay, this model where I've gone to minimize it is not a good representation of my function, at least at that point. So I shrink my trust region. I stay at this point. I don't move. I shrink my trust region. And I resolve the same model over a smaller trust region constraint. And there it is. I stayed at the same point. I've just shrunk my ball. Now I've minimized the same non-convex model, and I get that point. All right. Now you can see that I've decreased my function by a large amount. Okay. So then what happens? So now I've moved. This is my current point. So I'm getting closer and closer to one of my minimizers. Indeed, you can see that these contours of the function start looking more and more like my objective. So I keep going, and now I'm very close in that basin of attraction. And what happens is that my trust region ball keeps getting larger and larger because my model and my function agree more and more as I approach the minimizer. All right? And so I can, what happens here, in fact, is that the trust region constraint no longer makes a difference, because what I'm taking is exactly the minimizer of the quadratic, so the Newton step. So as I approach the minimizer, if it's a non-degenerate minimizer, these methods will allow you to take the Newton step, if you have, of course, the Hessian information in your model. So far away, you may not take the Newton step, but close enough, the trust region just sort of becomes irrelevant, and then you're just minimizing this unconstrained quadratic, and you're getting the Newton step. And in particular, you will start seeing the fast quadratic rate of Newton. Okay, so this was the path of iterates that we generated. But if you start somewhere else, you can do that at the other local minimizers. This is just to emphasize we are talking about finding local minimizers, not necessarily global ones. Okay, so going back to, okay, it's a bit of a problem now because I can't really go back through all the slides. So what I would like you to take away from the trust region framework is the following. It's an alternative to line search. There are state-of-the-art codes that are based both on line search and trust region. They are equally sophisticated and can solve large-scale problems. It's sort of which one you choose. It's a bit of a matter of taste. But I would say that for me, the trust region framework offers a more versatile way of dealing with non-convex local models. So it really allows you to take non-convex second derivatives and make use of them in the algorithm, because you can solve those models very well. And it switches more naturally between doing some kind of first order model to doing this kind of full second order models where you retain the fast convergence of Newton. Okay. Right. Can I keep going for another 40 minutes, or would you like a 5 minutes break? Hands up who wants a 5 minutes break. Okay. We are taking a break. Okay. So thank you for surviving until now. Right. So I will try to do the next part a bit more briefly, and I will skip some of the technical details, but they are on the slides and they are done in such a way that I think you can follow if you are interested. So I will try to give you a flavor of what do we do when we have a constraint problem, possibly with non-convex constraints. Right, so what are we talking about here? The first thing to say is that the way you should think about this question is, if my minimizer, my local minimizer, is inside my feasible region, right? So now I'm going to have something here, right? It's just not going to be just minimize f of x. I'm going to have some domain. If my minimizer is somehow interior to that domain, it's the same as if I had an unconstrained minimizer. Okay? These minimizers, right, when I look at them, because they are interior, they look like unconstrained minimizers. All right? So then you can essentially do the kind of thing we did before, provided you maintain feasibility. Okay? Things are not quite as simple as that, but keep them like that in your mind. Okay? The points we care about specifically here is points on the boundaries. Okay? So it's this kind of points that we saw earlier, that are not unconstrained local minimizers, but they are constrained local minimizers. All right? The first thing to notice is that, yes, the gradient was 0 for the others, the gradient of f. But here, the gradient is not 0. And the relationship as to what happens at first order, the relationship between the interplay of the constraints and the objective is a lot more complicated. So even characterizing optimality is no longer such a simple issue in general. The methods I will talk about, you can apply them for calculating any constraint minimizers, whether they are interior or not. But I want you to have in mind that essentially the kind of situation we are trying to characterize here is the situation where the gradient of the objective is not 0 at that local minimizer, but something else happens because points are on the boundary. And so I just want to briefly, and this is where I will skip a lot of detail, briefly tell you how we characterize optimality to first order. So we are no longer going to have just a 0 gradient. So I will talk about having f of x subject to, minimizing f of x subject to possibly nonlinear equality constraints, possibly nonlinear inequality constraints. And when I write this, I mean there are finitely many of it, and I mean them component-wise. Okay? All right. So we have a feasible set that's determined by the constraints of all admissible points. Right. So what is the analog of, sort of the analog of stationary points? Is so-called kk and t points. So the characterization to first order of constraint minimizers is complicated. And essentially, it's telling us the following thing, that the gradient of the objective at a kkt point is a linear combination of constraint gradients. So these are the gradients of my equality constraints. These are the gradients of my inequality constraints. The gradient of equality constraints, their coefficients come into this linear combination with any sign. Okay, so it's simply a linear combination. But for inequality constraints, the sign matters, and it's in fact a conic combination. All right. So roughly, sort of, gradient of the objective is a linear combination of constraint gradients. We have to have feasibility, and then we also have this property here that tells us that, in fact, only the constraints for which x hat is on the boundary are the ones that come into this characterization. So the constraints that are not active at that point, so equality constraints are always satisfied at all feasible points. But inequality constraints have this have this property that we could either be interior to the constraint or we could be on the boundary of the constraint, right? Well, because we only care about minimizers on the boundary, essentially, then we will see in a moment that this kind of the interior case does not come in. So from the inequality constraints, only the ones that are so-called active at that point, so they are satisfied with equality, for which the point is on the boundary, are the ones that matter. And this is just characterizing that situation. Okay? So where does this come from? Well, as we will see in what follows, for the approach for constraint problems is generally, let's try to make it unconstrained, because we know how to solve unconstrained problems. So here also, what we do is we associate to our constraint problem this Lagrangian. So the constraint problem is minimize f of x subject to okay, so we associate an unconstrained objective that looks at linear combination of constraints, and we see that then the KKT conditions are nothing but correspond to stationary points of this Lagrangian function at sort of the values of the coefficients y and lambda that appear in the KKT conditions, the sort of optimal multiplier values. So the components of the coefficients, so the coefficients that appear in this linear combination of constraint gradients in KKT, in the KKT equations, are called Lagrange multipliers. And this is the Lagrangian function. So there is here a lot of machinery that relates to duality theory and associates to our problem a problem depending on y and lambda, a dual problem. But I don't have time to go into all that. And anyway, for non-convex problems, this duality theory is only locally true. But we characterize, essentially, there is an unconstrained problem that underlies all this KKT characterization. So what do we say here? So let's just illustrate simply on this example. So we have quadratic contours here, and we have a feasible set determined by this parabolic constraint and this linear constraint. So the feasible domain is in here. And we can see that this is a convex problem, in fact, that the minimizer is at this point. The global minimizer is at this point. And at this point, orthogonal to the tangent is the gradient at that point of the objective. And then we can calculate constraint gradients. And we can see these are inequality constraints, okay, but they are both active at that point. So they will both come into this linear combination. And we can see that this vector lies in the cone spanned by these vectors. Okay, so indeed, if they were equality constraints, the sign wouldn't have mattered. But for inequality constraints, you want to have it has to be in the right direction to be a minimizer. So you can see here visually that this gradient lies in the cone determined by the two constraint gradients. So that's essentially what KKT is saying. And similarly, you can see that at this point, another point on the boundary, you have the gradient of f, and then you have the constraint gradients there. Only one constraint is active at this point, okay, just this constraint. And you can see that the gradient there is not a linear combination of any of those constraints. Right. So just a simple illustration. So what can we say? Can we say that any local minimizer is a KKT point? Is this a necessary optimality condition? Not all the time. Because this is a first order characterization, and it implies that essentially you can linearize constraints, and that a linearization of the feasible set, of the constraint set, gives you a good approximation of your feasible set. And that's not always true, because these sets can be very complicated if the underlying functions are nonlinear. And so you need some kind of regularity assumption on the constraints. There are various possibilities for that. And under those regularity assumptions, then local minimizers, you must have a KKT point to have a minimizer. Okay. Of course, if the constraints are linear, you don't need such constraint qualifications, and there are other cases where it's quite obvious. But in general, even this implication is not always true. Now, these first order conditions, if the problem is convex, they correspond to global. Well, there's no distinction between local and global minimizer, and then you characterize optimality to first order with these KKT points. What do we mean by a convex constraint problem? We mean that the objective is convex, but also the feasible set. And because of the way we wrote these constraints, to have these to be convex, you have to have them to be affine. And these ones, they actually, each one of them has to be concave. But that will give you rise to a convex feasible set. Right, so this is just briefly. Now, first order, again, is not going to be enough to characterize minimizers. And again, you have to look at second order and second order critical points of the Lagrangian. And there the story is quite complicated. I definitely don't have the time to go into it now. Right. So the take-away message from this quick overview is that when you go to constraints, you have to be careful how you characterize optimality to first order. And that is not that any local minimizer is such a KKT point. But in general, what the methods that I will talk about calculate for you is a KKT point. Okay? Right. Okay, so you can understand what follows, I think, even if you didn't understand anything about KKT points. All right? All right. So I will talk about two example methods for constraint problems. The penalty methods and interior point methods, and they both operate in the sense, in the following sense. They will make the problem unconstrained. They will associate a family of unconstrained problems that in the limit will converge to a solution of our constraint problem. And the first class of methods is a sort of exterior class of methods where you start from anywhere and converge to a feasible point. And the second class will generate points that are always feasible and converge to optimality in the limit. Right. So penalty methods. Right. So just bear with me here, because I think this one you will be able to follow. So minimize this function subject to equality constraint, possibly nonlinear, non-convex, anything. Right. So I will form a single parameterized family of unconstrained problems associated to this one. So I will put the constraints in my objective. And I will put a penalty term here depending on a scalar sigma. Okay. So my phi there, so that's called the penalty function. Okay. And it is f of x Okay, why do we have the half? It's just to cancel when we calculate the derivatives. It doesn't matter. Yeah. Yeah. Why do we have the square, though? That's my question to you. So why do we need the, well, we don't need the square there, but why do we put the square there? It's not differentiable otherwise. So f and c are smooth functions. And I would like to maintain smoothness of this objective so that I can apply methods I've talked about before. And so think of Euclidean norm here, so I have to square it to maintain smoothness. Right. So sigma is a positive parameter. Now, it's very hard to get onto satisfying nonlinear equations. And so having a feasible point of this, even just without the objective, is hard. And so this is sort of the idea here, that I will proceed to a sequence of infeasible points, and I will converge to a feasible and at least stationary point in the limit as sigma approaches 0. So what happens in this objective? This acts as a weight on the constraint. So as sigma goes to 0, this term gets larger and larger. So when I minimize this, I force more and more this function to minimize my constraints, to minimize the error in my constraints. Okay? So to force feasibility. Okay. Of course, this function, because all these functions involved here are non-convex, this could be, this could have other solutions than the solutions of my original problem. But there is a correspondence. And in particular, you can see that if I write my first order optimality conditions for my penalty function, so now I will just do unconstrained minimization applied to phi. Then what I get here is 1 over sigma Jacobian of the constraints transpose Cx. So essentially, when I compute a stationary point of my penalty, this essentially corresponds to the KKT conditions for my problem with a certain estimate minus C over sigma of the Lagrange multipliers. So there is a just sort of even algebraic correspondence that way, but we'll see in a moment more. Let me illustrate this. So I'm plotting the quadratic penalty function for various values of sigma. So sigma is large, right? So these are the contours of my quadratic penalty associated to this non-convex problem. So my problem, the constraint is this one here, the red one, and this dot is my optimal solution of this problem. So if I minimize this, so I write my quadratic penalty, so it's going to be this plus 1 over 2 sigma, well, this with 0 residual squared. And then the first one, for sigma equals 100, the first phi sigma is these contours here, and the minimizer is somewhere here. So it's quite far away. As sigma is decreased, right, then the minimizer will be here of this quadratic penalty function. And now I keep decreasing my sigma. These are the contours of my quadratic penalty again. And this is the minimizer is somewhere here of the quadratic penalty. So I am getting closer. But you can also notice how the contours of the quadratic penalty elongate more and closer towards the constraint. In particular, in this side, so along the constraint, sort of orthogonal to the constraint, the quadratic penalty grows very fast. And you can see that even here. And you can see that when sigma is this small, it looks even visually that I'm getting closer and closer. All right. So this quadratic penalty is going to have this kind of steep walls around the constraint. So it's going to grow very rapidly in some directions and much slower in others. So what would be a method for solving my constraint problem? I'm going to choose an initial sigma 0 value for my penalty parameter. And then I will minimize approximatively to some tolerance epsilon my quadratic penalty. So I will minimize this function here for that fixed sigma. This is now an unconstrained minimization. So I can apply what we've spoken about until now, line search trace region. Then I'm going to decrease my sigma and minimize again. OK, so you could ask me, why not choose a sigma and minimize, and that's it, right? Why do you do this sequence of decreasing sigmas? Because it really helps, because these problems get more and more ill-conditioned. Well, I'll talk about that a bit more in a moment. But essentially what we do is that once we've minimized this phi sigma, we've gotten an xk, I shrink my sigma, and I start my next minimization from my current guess. So we apply what's called the warm starting procedure. So I start my new minimization of my next penalty function from the current best guess of my solution for my current approximate minimizer of sort of the previous penalty parameter and function. So sigma goes to 0 and is decreased by, say, a fixed fraction, 0.1 in each iteration, or more rapidly, maybe when you are zooming into the solution. So indeed, we can apply the methods from before, but we have to be a bit careful because of this kind of rapid growth. So if you do the usual truss region, for example, and you have a ball constraint in one of these plots here, right? If I put a ball here, you know, and centered at my iterate, then I will have possibly very rapid growth in my penalty in some coordinates and very different in other coordinates. In other words, essentially I'm losing on the scaling here. I'm getting a sort of poorly scaled function. And so what I need to do in my trust region is to sort of elongate my trust region shape to counteract this effect. But this is all done work. I mean, you can find in the literature how to do this. You just scale your trust region appropriately. And so indeed, we can show that these methods converge, and they're quite, well, if the method behaves well, we can show that it gives us what we want, essentially. So if what we do is we solve each of these penalty minimization, irrespective, in fact, of the starting point, we solve it to some tolerance epsilon k. And this tolerance has to increase with each minimization of, or at least overall, has to increase when I minimize my penalty function. For each of the penalties, I solve it to more and more accuracy by some kind of trust region or line search. Then what we can show is that if the iterates converge, and if I have some constraint qualification assumption, some regularity on my problem, then this limit point of the iterates is also a KKT point of the problem. Okay, so this is different a bit than unconstrained. For unconstrained methods, we just got convergence from any starting point to zero gradients. But here, we have to actually assume that there is some kind of convergent behavior there. And then that limit, we can say things about it. Now, there is a problem with these methods. You could see from those contours that you have increasing ill conditioning in the problem. This steep kind of, the problem gets more and more poorly scaled because you have this very rapid growth in some directions and slow growth in others. And what that translates into your second derivative matrix being very ill-conditioned. So the condition number of that matrix can be very large and growing with sigma. It blows up with sigma, really. However, there are ways to compute the, say, Newton-like directions for this function that you're not affected by this very much. So this has been also well researched. And the way to do it is either you do a change of variables or you can do a sort of primal dual method where you work with both the primal and the dual variables and apply Newton method to both. So you have a larger system, but it's you can then do better in terms of the conditioning of your system. Okay, so this is just to give you an idea. Now, we chose a smooth penalty. You can work with non-smooth penalty. And they have a property that, in fact, then you don't need to drive this sigma to 0. There is a finite sigma for which minimizers of phi correspond to minimizers of the problem. In the quadratic penalty case, you have to drive sigma to 0 to achieve feasibility, essentially. But for inexact penalties, you can show that there is a fixed sigma for which this correspondence occurs. Of course, you don't know this sigma a priori, but it's not at 0. So the conditioning is could be less of a problem, but then you have to deal with the non-smoothness when you solve your penalty. But these are very much used approaches. So this L1 penalty, for example, is very much used. And Fletcher, for example, has pioneered that in the last decade very much for non-convex. Okay, so let me tell you in 10 minutes, or maybe a little bit more than 10, but not too much longer than 10, about inequality constraints. So we've talked about this method that approach the constraints from the outside. Now I will talk about a method that approaches constraints from inside, or approaches the solution from inside of the constraints. This is mostly for inequality constraint problems. So essentially, we think of inequality constraints a little bit as sort of easier to satisfy because they will supposedly generate a bigger feasible set. So it's not such a crazy assumption to think, though it's not trivial, but it's not impossible as hard as it is for equality constraints to assume that you can start with a strictly feasible point of all your inequality constraints. And this is what interior point methods do. So now we will look at a different kind of unconstrained family of problems that we will associate with this inequality constraint problem. And these are the so-called barrier functions. So what I will do is each of my inequality constraints, I will put it in a log term. So I will associate here to my original problem this problem. F of x minus mu and sum of log of ci's. Okay, subject to c of x being positive, but you can sort of ignore this because we will force it and sort of think of the log here forcing a non-negative argument, a positive argument. And so we think of this, if we don't have equality constraints, the problem, we think of this as an unconstrained problem. So why do this? Because, so assume that my iterates are strictly feasible. So Cix is strictly, Cx is positive. Right. So I'm inside my feasible region. What does the log do? The log prevents me from reaching the boundaries when mu is large. If ci of x is close to 0, log of 0 is minus infinity, with minus is plus infinity. So when I minimize this function, the minimizer of this function cannot be close to a boundary because the function there is very, very large. All right? So the minimizers of this are sort of bound to be interior. So if I minimize this, I'm sort of staying away from my boundaries. It is like I put a barrier around them and I prevent my points to approach it, sort of. Okay? So why would I want to do that? Because I have a sort of combinatorial aspect to my problem. When I have inequalities, I have to find which ones are active at the solution. And this sort of avoids all that aspect, all that combinatorial aspect. A little bit more of that towards the end. So, right, so I have this log barrier. And, right, but hold on a moment. I said I'm staying away from a boundary, but at the same time, I'm looking for a boundary solution to my original problem, right? So I have to do something else, something more. So yes, when mu is large, I'm staying away from boundaries. But as I decrease the weight on my log terms, right, I will be allowed to approach a boundary. And because I have this term in the objective as well, I will be forced to approach my optimal boundary. In principle, okay? A lot of things can go wrong because I have a non-convex problem. And for example, this problem could be unbounded below, even if my original problem is bounded. But if things work out, this is the idea. All right, so this is just an explanation of what I've already said. Okay. Now, let me illustrate again. So I have a quadratic objective and then this constraint. So the constraint is not, less than or equal to 0. So it doesn't contain the origin. So the constraint is this set here, right? So above this red line. And this is the barrier from mu equals 10. So the minimizer of the barrier is far from this constraint here. Then I decrease mu. The minimizer of the barrier is here, okay? Then I decrease mu again, and sort of I'm starting to approach the minimizer of my problem. It's a bit hard to see on this plot, but in fact, you do get blow up here at the boundary, but it's just very, very hard to see. So you do approach the minimizer, but you will get blow up at the boundary. It's just that the minimizer will be sort of closer and closer to that boundary. But you do get, more and more ill-conditioned problems. Okay, so we call the central path sort of the path of minimizers of these log barriers as a function of mu. Is this path well defined? Well, I've given a theorem here. Please don't read it now. That says that if I'm sufficiently close to a non-degenerate minimizer of my original problem, then this path is well defined for sufficiently small mu. But, okay, so let me illustrate this path. So here's a quadratic objective with some linear constraints. So this is my feasible set. This is my objective. And this line here, in fact, goes from mu equals infinity to mu equals 0. And it's a continuous path formed of the minimizers of the barrier. Each of the barrier functions is convex, so it has a unique or well-defined minimizer that's global. And so this path is this path of barrier minimizers. And you can see that as mu goes to 0, it goes to the solution of my problem. Once I change this a little bit and my objective, say, is not convex anymore, then a lot of bad things can happen. So my central path is only I'm going to have a central path there, but I'm also going to have another bit there. And so you start having these nice properties. You only know that if your minimizer, original minimizer, is non-degenerate and so on, sufficiently close to it, you will have a well-defined path. But still, you know, we just do it in non-convex optimization. And actually, it works surprisingly well, even if we lose these properties. So what does a barrier method do? You have to have a strictly feasible point, and it generates a sequence of decreases in mu values, and you just minimize each of the barrier functions. Usually, just like for penalty, starting from the previous solution. Okay. Again, you can minimize f mu using unconstrained minimization, but you do have growing ill conditioning. In fact, it used to be, it was so bad, and it is so bad if you do nothing about it, that these methods that were invented in the 60s completely fell out of favor by 1990s. I mean, nobody was using it anymore because this ill conditioning was really killing you. It was worse than for penalty methods. Despite the fact that we can have a similar convergence result as for penalty, you minimize your function to some accuracy, your barrier to some accuracy. It's an unconstrained minimization. This accuracy increases as you solve the problem. You have this non-degeneracy assumption. Again, if your sequence converges, you can show that you converge to a KKT point. But numerically, really, your linear algebra is going to have problems. And this is, I have a couple of slides on this. So again, the Hessian matrix, the condition number blows up, and really it affects your computation, and you can see it happening much more. And you also have another property that if you do this natural initialization of each barrier minimization from the previous point, from the previous approximate solution for the previous barrier, you actually will not have fast convergence. You are not able to take Newton steps, full Newton steps asymptotically to give you quadratic convergence. So this slide tells this in a longer way. So really there were a lot of problems with these methods. But because of what happened in linear programming, not in nonlinear programming, we were able to overcome these problems. And the solution is this kind of primal dual methods, which I don't have time to explain. But essentially, we are not going to work just with x in calculating x in the Newton direction. We are also going to work with the dual variables. So we have to compute Newton directions for the dual variables as well. And if you do that, actually all these problems can be overlooked. You still see, if you go and implement a primal dual interpreter method, you're still going to see ill conditioning coming in. But it's going to be far less problematic. And there are various ways to go around it. So you can sort of overlook it when you calculate your Newton direction. So this is all sort of doing that, which I don't have time to explain. But essentially, there is a lot of good non-convex solvers there. IPOP, Nitro are really, really powerful solvers. And I cannot end this lecture. So these are the last two slides, okay? Before I tell you a little bit more here. So this story with interior point methods is very interesting because what happened was, in fact, that the resurrection of interior point methods for nonlinear problem arose because of linear programming. So it was discovered that that interior point methods are polynomial algorithms for linear programming. And in that context, all these primal dual variants were developed. And then people started to use them for non-convex problems and found them efficient for non-convex problems, even though all this primal dual framework is only local in the non-convex case. So there is a very nice story as to how all these interior point methods came about, and they are really, really successful at solving linear programming problems, where a lot of things are easier. You don't need all this. You don't need to solve each of the barriers to higher accuracy. You only take 1 Newton step, for example, and the complexity can be quantified. Okay. Right. So I've tried to give you more of an overview for unconstrained problems of the state-of-the-art methods, and for constrained problems, just to give you a taste of an example of 2 classes of methods that are state-of-the-art. There are others, and people use usually a combination of them. And these are some of the methods that are, that a usual course in this would contain. You can find a lot of software that will solve these kind of problems for you. I don't think you need to necessarily implement if you can do, say, matrix vector products efficiently, or at least if you have quite accurate gradients. But if you don't have accurate gradients, then you will not be able to use this kind of methods. I mean, accurate or at least computably to sufficient accuracy with finite differences. If you don't have that, then you need something else. Okay? So if you have an optimization problem, you sort of need to think about what kind of information do I have about my function? Do I have derivatives? Are they accurate? Is this a noisy problem? If it's a noisy problem, you can't use what I've said. So there is another sub-area of optimization called derivative-free optimization that deals with this kind of case where you can't compute accurate derivatives, and your underlying function could be smooth or not. These methods are built very similarly to what we saw before. Well, very similarly in the sense that they do compute local models, but using interpolation. And there is good code out there for this, but they don't scale to as large a dimension as for derivative-based. I have not talked about global optimization, where the situation is pretty dire. So if you really need the global solution of your optimization problem, your problem better be convex, I would say, or low dimensional. The scaling of these methods is not great, but for smaller scale problems, you can get some good codes there. And really, there are a lot more specialized methods for certain subclasses, but again, time is very limited for that. So, okay, please do ask me questions. Please do write to me if you have optimization questions. And I hope to interact more with you during this ATI program. Okay, thank you.